Good afternoon, everyone. My name is Wantida from Mae Fat Luang University, Chiang Rai, Thailand. Let's come back to the small part of my work. I am pleased to share the work, additional work from waste as well. According to Professor Rim and Professor Wani, here is the work about the mango kernel seed. One moment, please. I'm not sure if I should use this one. Okay. This work, thanks to my student, the work is about the mung bean protein. Okay, sorry, could you please go back? Yes, the mung bean protein isolated, as people know that the mung bean is really the bean that everyone knows, and it's abundantly available, and we normally use it in our daily food, but not much about the protein. So today I would like to bring another point of view about the film that can be developed from the mung bean protein isolated. And also we also talk about the mango kernel extract that we're gonna add in order to add the antioxidant properties to the film. Okay, let me begin my presentation. Okay. This is just the outline. Again, as Ajahn Professor Rim talked about that early this morning, the food waste and the byproduct especially poses a serious threat to the environment. In this case, I'm talking about the mango waste that normally it is not useful. About, I think about 40% of the mango waste do nothing. We just do the landfills and stuff, and it will go to the sea eventually, as earlier mentioned about the microplastic, and eventually it will be with us all in terms of our food. So today, we really think about what can we do with those things. We really go for the bioplastic. Is it a real solution for us all? Because maybe we may have to think about what if it is not the option, the best one yet? Because we need water. We need something else to grow those alternative bio products. So that is why I came to think about the greener raw materials, especially the Thailand. We have a lot of agricultural waste, especially continuous with the mango. We have that raw materials. So both mung bean is really a cheap option. It's really cheap, like 1 kilogram is only probably less than 500 won. Yes, for 1 kilogram in Thailand. And we normally use that for the noodles, just for the production of the noodles. So we use mainly its starch. So the leftover part is the protein. I didn't put it in here, but let me talk about that a little bit. The protein in the mung bean is kind of go to waste because of the byproduct. So here we come to think about what can we do with those protein. It's actually the protein that almost a complete source of the essential amino acid for the protein, in the mung bean. Together with the rice, actually it can combine and complete all 9 essential amino acids for us all. So that is why we come to think about the mung bean protein isolate. In this case, we use the Thai mung bean protein. And for the mango kernel, we use the shok anand. Okay, and as you can see from the picture, the mango seed kernel is around 20 to 60%. So it's all go to waste, not including the peel. Another part is the peel. That is maybe something else like pectin or something, but now I'm focusing on this mango kernel, mango seed kernel. And out of the mango seed kernel, the inside, the inner seed is about 75%. How much? Can we picture? The whole year, it will be 4 to 18 million tons a year. And that 75 with 60%, that is quite a number for the waste that go through the landfills or just food feed, animal feed, sorry. And here we bring the two things to develop and characterize the physical properties of the packaging, but from the byproduct of the mango and mung bean protein as the waste or the byproduct from the starch extraction for the noodles. Okay. So this is just a small part of the small work that we've done, and we hope to continue this. I mean, for the commercial, like Professor Wani did with the mango, the lignin thing, and we just extract the mung bean protein at some certain condition, and then we formulate that with the mango kernel extract, 0 to 5%. I mean, 0 means the control one, and then we just study the regular property for the film, and we also did the morphology and migration, small migration test because initially we would like to make something that edible. What if we can eat those things? So we just would like to test in the fatty food a little bit. So this is just, I'll just go real quick about this because it's just a preparation process. So we do the mung bean and then we just dry and then keep, and the yield is about 95%, I mean for the flour. And then we bring those flour to extract the protein. And we got the 85% of the protein, so it's kind of isolated. And then the yield is around 13%. This is for the film base. Okay, so we did the protein film from the mung bean protein isolate that was isolated from the byproduct. And then we do the extract of the mango kernel. As we see, you can see that is a small picture of the mango kernel, and then we pulverize, make a powder, and then we extract with the ethanol and freeze dry to make let me call MKE. The yield is around 7 to 9% depending on the production batch. And to produce the film, just use the cast drying method. And we, with the help of the glycerol, and it helped combine everything together, and we got the film. And we conditioned the film at 25 degrees Celsius, and which the RH control. So finally, the film shows that it's appear that when we add the mango kernel extract, the film appear to be darker color, and but still, the opacity is not that much different. Take a look from this. The color is lean toward the red and the yellowness, and the opacity a little bit different, like increasing, significantly increasing. So it's confirmed with the appearance here. And for the surface morphology, you can see that the control film is kind of smooth as the protein combine well, but when we add up to 5%, you started to see it's kind of a little dot that is not fully combined, probably because of the excess amount of the mango kernel extract. And for the thickness, as we can expect that the higher the amount of the mango kernel extract we add, the higher the thickness. And for the moisture content, it's not that different. And for the water vapor permeability, as we all expect that around 3 to 4% the tortuous path may play a role, that it is delay the traveling of the water vapor, but however, at the higher 5%, it's become shorter. Again, it could be of the hole in the film at the higher percentage of the mango kernel extract. And for the mechanical properties, tensile strength, and the elongation at break, the higher the amount of the mango kernel extract doesn't alter the tensile strength. It's still be in the kind of in the same range, but it's a little bit different from the control one. Okay, and for the elongation at break, it's reduced significantly reduced its elasticity. And for the seal strength, we try to heat seal, because even we aim to make the small sachet for the seasoning, like noodles, instant noodles or some sort like that. And then we try to make the square small sachet by heat seal and fold type. And we found that actually before we get this number, we try it at different temperature and different thickness as well. But the result doesn't show here. We found that at the higher mango kernel extract, the seal strength is the highest. Yes. So with the and eventually, because we would like it to be edible, so we would like to try at what temperature we could do to see the solubility of the film in the water. And we found that the control film is kind of dissolve faster compared to the other treatment. And at the highest MKE 5%, the solubility is the lowest one, probably because of the availability of the bond. It's not available to bond with the water, so it's kind of faster. Higher hydrophobicity when you add more MKE at this point. So, and talking about the expected antioxidant properties, we add the mango kernel extract, and to expect that we can make it higher antioxidant ability. So we measure the TPC, and as we expect a higher concentration of the mango kernel extract, the higher amount of the total polyphenols, and also it's confirmed by its activity by the DPPH. And for the last one, we did a small test, not on every solution. We picked only the 95% ethanol because we aim to use something with the higher fat content. Probably the instant food, noodles. So we picked this, and we found that in the 95% ethanol, the film still the antioxidant properties is not migrate that much compared to the water. That means if we put this sachet with the seasoning, and then we put it in hot water, it can be deducted. It might be able to completely dissolve, as you can see from the release the antioxidant properties from the film. So we hope that it can help protect the oil in the sachet. To reduce the waste, that we don't need to throw away the small sachet when you eat the instant noodles, something like that. But we are not go fully, completely test the whole system just yet. So hopefully we can complete that in the near future. Yes, I think. That is the message that we got today, that using the mango kernel extract can help increase the antioxidant properties of the film, and for the application, the developed film can be dissolved in the water and can be withstand the fat. So that means it can hold the fat inside its sachet. And we prove that it can be heat sealed as well. So the next phase that we hope to complete is to test with the real system. We used a small prelim test, but not the whole the complete thing yet. Yes, and that is all of my presentation today. And thank you so much, everyone, for listening to my small sharing today. Thank you very much.